Hello everybody and welcome back. Root Beer here, and we're going to be wrapping up our 2012 Galois paper with question number 4. So if you haven't given it a try, I would strongly encourage you to pause the video and try it out. We've got a light bulb part and then 2 written parts here. Alright, there isn't a D, nope. Alright, so what have we got? In Town A, 5 students are standing at different intersections on the same east to west street as shown. So we got Abe, Bo, Carla, Denise, Ernie. The distances between adjacent intersections are shown in kilometers. So 1, 2, 4, and 7. The students agree to meet somewhere on the street such that the total distance traveled by all 5 students, try to underline that again, is as small as possible. So we want to minimize the walking distance or the travel distance for these people. Where should the students meet? Okay. So initial thoughts might be to sort of average things, although it might have to be some sort of weighted average, because Abe, Bo, and Carla, they're really close together. Ernie's got a long distance to walk no matter where they sort of meet. It wouldn't make much sense to put our meeting place close to Ernie. He wouldn't have far to walk, but then we'd have 4 people walking pretty far to get there. Now, they gave us Abe, Bo. They gave us all different names, so we can just say A, B, C, D, and E, and you are more than welcome to do that on a test. So we put A here, E here. And actually, just while I've got them here, no matter where I put my meeting place, well, moving it to different locations might make Abe travel far, Ernie will travel less, but in total, they're both going from the end points all the way in. So that's sort of an interesting observation we can make. It doesn't really matter where our meeting place is in terms of how far Abe and Ernie go, because they sort of cancel each other out. We have Bo here. What was it? Carlos and Denise or something like that. Carla and Denise. My apologies. So 1, 2, 4, and 7. So we might say, let M equal the meeting place. Or there could be more than one. There could be sort of a range of meeting places. Anywhere between Carla and Denise could work just fine. Something like that. Who knows? But AM plus ME equals the total 1 plus 2 plus 4 plus 7, which is 14 kilometers. So we don't really need to worry about the distance Abe or Ernie travels. They're sort of taken care of. So what matters is, well, where is M? Is it going to make Bo, Carla, and it was Denise, right? Where can I minimize their distances? That's the challenge now. And it looks like we sort of have a few possibilities. Could M be between A and B and C, C and D, or D and E? Or I guess it could be, maybe for some reason C is where we need to go to because it just happens to be in the middle of the order. Who knows? Or D, because D is actually halfway between the 2 distances, the 2 endpoints. I'm not entirely sure what we need to do, but we could take a look at some of these possibilities. So I'll get out the blue here. Suppose M were here. Somewhere in between A and B, for example. Well, wherever it is, Denise is going to have to walk there, and that's going to be at least a distance 2 plus the distance 4. So Denise is walking at least 6. Bo is walking some potentially non-zero amount. Well, at least 0. Because if M happens to be on B, then Bo is walking no distance. And Carla is walking at least 2 to such a place. What if it were over here, at the other end point, put M here? Well, Bo is then walking at least 2 plus 4, so at least a distance 6. And Carla's walking at least a distance 4. and Denise is walking at least a distance 0. I've got these on the wrong side. So automatically I know the green possibility is out, because that would mean everyone's walking at least 10. Actually, we could give upper bounds as well. But everyone's walking 10, whereas, I mean, even if I just put M on B, people are walking 8. But can we do better than that? I think we can if we place M somewhere in between B and D. So, for example, if I put M somewhere in here, just like Abe and Ernie cancel each other out, Bo and Denise will cancel out, and they will add up to a total of 6, and so then it's really just how much walking is Carla doing, and we can minimize that by moving M to where Carla is. So if I place M at C, I can write this up, I suppose. Well, it's a light bulb, so I don't want to, but maybe I'll need to do it for the B and C parts. I probably could have read the B and C parts before continuing on, but if M is on AB, then BM plus CM plus DM is at least 8. If M is on DE, BM plus CM plus DM is at least 10. If M is on BD, BM plus DM equals 6. So minimize CM by letting our meeting point M equal C. So what were they? They were students, right? The students should meet at C. That way Carla doesn't have to do anything, and it's going to... Did they want us to tell them the minimum distance? Where should the students meet? They should meet at C. That's all it is. But it's going to be 14 plus 6. It's going to be 20, the distance that everyone walks. Okay, so that was kind of interesting. It turned out to be Carla because Carla was in the middle. That's kind of cool. Okay, what do we got here? In town B, there is an even number of students. So there won't, if it's anything like question A, we won't be able to say, the middle person. So in town B, there's an even number of students. The students are standing at different intersections on a straight north-south street. The students agree to meet somewhere on the street that will make the total distance traveled as small as possible. With justification, determine all possible locations where the students could meet. We want minimum distance. Okay. So it's a north-south street. I'm just going to give myself a bit more space here. So we're going to have north-south street. So you could have like student 1, student 2, but maybe a big gap, student 3, and then student 4, and student 5, and student 6. I don't know how many, but they said an even number, right? So, before I, generalize this more, let's just talk about what would happen if there were just 6 students, right? So I think the same reasoning should apply. It doesn't matter where the meeting point is in terms of S1 and S6, they will always add up to the total distance. Now, if the meeting point is above S5 or below S2, if I call these distances, I'll call this A and then this distance B. Everyone's walking at least, so A plus a bit and then B plus a bit. Everyone's walking at least A plus B. Or if we're walking here, S2 is going at least A and S3 is going at least B. But I think anywhere in between here should work. Yeah. Because anywhere in between here should make the distance S4 and S3 walk should add up to B, and S5 and S2 should add up to A. Yeah, so it's kind of... It doesn't matter how far apart they are, it just sort of matters who the innermost people are. And in the last one, Carla was the innermost person. But how can we write this up? What do we want to say? Maybe number of the students. S1, S2, all the way up to... I'll use subscripts, actually. S1, S2, all the way up to SK minus 1, 2K minus 1, and S2K. Why S2K? They tell me it's an even number of students, right? And they didn't say how many students, right? They didn't say... No. Just some even number, so there we go. We've got some even number. Okay, traveling north. So just give them some order. Okay, so we claim any meeting place between the intersections where it'll be K and SK plus 1 are, will do. And I'll say inclusive or including those intersections. Okay. So let's just clean up that word there. Alright, so I think this should work. Here's what I'm going to do. I'm going to say... let us define some distances. In kilometers, just like the part A was technically in kilometers, although we didn't use that. So I'm going to say distance I is going to be SI to S2K minus I. 2K plus 1 minus I. So, for example, distance 1 is how far as student 1 and student 2K are apart. Distance 2 is how far away student 2 and student 2K minus 1 are apart. We're just sort of going inwards. So this is D1, this is D3, this is D2. Alright, so that's the idea. Okay, so... how do we want to say things? So, I suppose we could, if the students meet so there's going to be two parts to this. I want to show that some point M in between. So if the students meet at M, and M is on segment SK plus 1, then the total distance, I'm going to tell them what the total distance is, and then I'm going to show that if M were anywhere else, the distance would be bigger than that. So the total distance the group travels is D1 plus D2 all the way up to DK. Alright, so why is that the case? Well, M is on SK plus 1, the line segment there. So, DK is SK plus 1, but that is the same as SKM plus, because M somehow divides the segment. Since SK to SK plus 1 is on segment SK minus 1, SK plus 2, DK minus 1 is that total length. But M breaks that down. And you could probably stand to have a picture like we have a little had earlier. I'll actually draw it on the next page. And so let's say similarly, M is on S1, S2K. So distance 1 happens to be the sum of the distances that student 1 and student 2K will travel. So I'd say S1 down here, S2K plus 1 here, S2K minus 1, S2, S3, maybe S2K minus 2, all the way down in here, SK, SK plus 1, and then we can put M over here. And you could call it D1, D2, D3, all the way down to DK. But the total distance traveled is the distance from S1 to M plus the distance from S2 to M all the way up to the distance student 2K is from the meeting place M, but that's D1 plus D2 all the way up to DK by what we just explained on this page. Okay, so now I know that if M is somewhere in between or including these two intersections where student K and student K plus 1, but in between the middle students, I know the total distance there. Now what we want to do is show if M were anywhere else, then students would be traveling further. Okay. So how are we going to do that? Well, suppose another M, and if you wanted to, you could call it N or M prime or something like that, minimizes the distance further or equal to, you know, just if there's any other place that will get the same distance. But is not on segment, say, S1 S2K. So what I'm going to do is I'm going to say, suppose there were some other point M, I'll put it in blue so it stands out, M up here that's beyond this. What would we do? Well, then S1M plus S2KM is going to be greater than, strictly greater than D1. And similarly, I think I might need to do a picture to better explain this. Just trying to think if there's a cleaner way to write this. Let's say is on segments S1, S2K, all the way up to SI, S2k plus 1 minus I, but is not on segment Si plus 1 S2k minus I all the way up to Sk k plus 1 I for some I in between these values. So there's some segment, and it could be the innermost segment. Heck, it could even be the outermost segment. Who knows? So I'll let I be 0 to say it's not on anything. Then what have we got? As a picture, got S1, S2K, and then in SI, S2K plus 1 minus I, SI plus 1, S2K minus I, and it keeps going further and further in SK plus 1, SK. So what are we saying? M is somewhere here, or somewhere here, in one of those two spots. And I guess we could say then S1M plus S2KM still is that total distance D1, all the way down to SIM plus S2K minus plus 1 minus I, and that'll be DI. But we see, and it doesn't hurt to have a picture, so just say, M is here. Turns out the total distance is definitely more uh, 2k minus IM is more than DI plus 1 all the way inwards. Because you'll always be traveling outside your little band, your little segment that these two numbers work on. So then the total distance is then seen to be strictly greater than all these values. So the M's on segment SK plus 1 of the street do minimize the total distance. In fact, what we've shown is, well, I guess all we've done is show it for even numbers, but you could easily do the same thing for odd numbers, just have the middle odd number. So let's say for even number, any point between the innermost two when ordered will minimize distance. And I guess I'll also say, if I need to, I'll justify this. I don't know what C part has, actually. For an odd number, the middle point. That's what we saw in part A, Carla. And we could show that. Just go here and add in a middle point in between them. And then we just need to minimize that distance to M, and so you make that 0. The middle point, when they are ordered, gives the unique minimum. Okay. So that describes our answer to B, anywhere in between the two innermost students. Okay. Now we got town C in part C. The streets run north, south, east, west, forming a positive... Oh, we're going to have to minimize it horizontally and vertically, aren't we? Because that's why they made us do east, west in the first one. Alright. But let's actually... Let's read this to make sure I'm right. positive XY with intersections every 1 kilometer apart as shown. Great. 100 students are standing at different intersections. The first 50 students, looks like they're telling us where the students are, numbered 1 to 50, stands so that the student numbered K stands at 2 to the KK. So at 1, 2, and then 2, 4, and then 3, 8. Alright, so... Oh, sorry, I've got the XY coordinates wrong there. It'll be 1, 2, 2, 4, 3, 8. So there'll be someone out there all the way at 2 to the 50. Okay. For example, student 5 stands at 32, 5. Alright. The remaining students, numbered 51 through 100, stand so that the student numbered J stands at J minus 50 to J minus 100. So student 51 will be at 1, 2. And then the next one will be at 2, 4, and then 3, 6. Okay. Students can only travel along the streets, and they agree to meet at an intersection. So our answer will be an intersection. That will make the total distance traveled by all students as small as possible, with justification determine all possible intersections at which the students could meet. Well, there's an even number of students, whether or not you organize them north, south, or east, west. So I could see there being as many as 4 different intersections all around sort of a square. Maybe not, could be 2 intersections in a line or a line like that, or maybe there is just a single intersection they meet at, but those are the possibilities. There's no way it's going to be 3 intersections, and by realizing that, I can at least sort of double-check answers that I eventually get through calculation. Okay, but because of the work we did with even students in B part, we can sort of apply this result, this even middle minimum distance theorem. Okay. So first thing I would say is since students only walk along the grid, they did say that, right? Only travel on the street, on the grid, whatever. Only walk along the grid, we can break the problem into the minimum horizontal distance and minimum vertical distance. I don't think this needs to be justified. If you wanted to give a sentence or two justifying it, you go right ahead. You could even talk about like the taxi cab metric if you know that. But I think it's obvious. It's a grade 10 paper. Don't work yourself too much about this. So as we sort of proved in B, for an even number of points, to minimize the distance in a line, we take any point between the middle 2 values when ordered. Okay, but I will point out that since C is asking to meet at intersections, we will limit ourselves I guess ourselves is one word, isn't it? We will limit ourselves to integers. So, for example, if it turns out that the innermost are 10 and 11, I'm not going to say, well, they could meet at 10.5. That's not at an intersection. That wouldn't be at a crossroad. So it would be 10 and some height, and 11 in some height. That's the idea. On the other hand, if the two middlemost numbers were 10, then you'd get duplicates. And we can get duplicates. Because as we sort of see here, there are two things that are at the same height as 2. Only one at the height of 1, only one at the height of 3. But there will be 2 at the height of 4. 2, 4, and 16, 4. For example. Okay, oops. Wrong button. So, I don't know, let's work horizontally. So my numbers are 2 to the 1, 2 to the 2, 2 to the 3. Now these numbers are going to get pretty big pretty fast, so we'll know what the last few are. And then we also have 51 minus 1, 52 minus 1. Yeah, we just keep going all the way up to 100. Now, I know that 2 to the 7 is... Oh, sorry, it wouldn't be 100, it'd be 50, wouldn't it? 2 to the 6 is 64. 2 to the 5 is 32. So... 2 to the 6 is 64. So the last 50 minus 6 plus 1, so that's 45. Or not the last, let's say the largest. Horizontal values are 2 to the 6 all the way up to 2 to 50. So really we were asking ourselves, where does 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5, where do they fit in? So there are 5 powers of 2 to deal with. So those 5 plus the first 32 integers here equal 37. So the 38th integer is going to be 33, then 34, and so on. Okay, so 38th position is 33. The oops, bouncing around here. Where are we? There we go. All right, so 33 to 34. So the 38th position. I can go back, right? Yeah, okay, there we go. So the 38th position is 33. The 39th one is a 34. It was 45, so 50 is the 100th position. No, this is the 100th position. And then this is the 56th position. 56, 57, 58. Yeah, that would count up to. So the 55th position is 50. So we just sort of need to count down. What we're looking for is the 50th and 51st. So 49, 48, 47, 46, and 45. Yeah, we just subtract 5 each time. So that tracks. So horizontally, meeting at an x coordinate of 45 or 46 will minimize the distance. Okay, so that works out. And then what about the vertical distances? Well, let's start again. Vertically, what are we going to have? You go up by ones for the first 50, and you go up by twos for the next 50. Alright, so we'll have, so vertically you'll get 1, 2, 3, all the way up to 50. And you'll also get 2, 4, 6, all the way up to 100. So the 25th one here is going to be 50. So 24 of those, 26 of these, 27 of them. Last 27 are 50 plus. So I guess we could count down and every even number has 2. That's where we were earlier. Lately my notepad is, in the middle of recording, it'll just decide to leap 3 pages ahead for some reason. I don't understand it. Anyway, where were we just at? So 25, 27. So it's sort of 50 and 50. And then 52, 54, all the way up to 100. So 100 is the 100th position. This one here is the 52nd. No, it's not the 52nd, it's the 26th. Wait, no, what? Oh, I'm having trouble keeping track of what it is that I'm doing. So there's 26 of those. So 98 should be the 99th one. So divide by 2 and add 50. So this should be the 77th. This should be the 76th. This is the 75th and 74th. 49. Then you'll get 2 48s. So 73rd, 72nd, 71st. 47, 2 46s. 45, 2 44s. It's going to take a while. I don't want to try and get another formula in my head. I just worry about being slightly off. I always hate when I'm slightly off. 69, 68. We're not that far, I guess. 67, 66, and 65. So the 65th largest y coordinate is a 44, but it also is the 66th largest. 43, 42, 42. 41, 40, 40. 64, 63, 62, 61, 60, 59. We're getting really close. 58 will be a 39. Then we'll get 2 38s, one coming from the 69th student standing on a corner, and one coming from the 38th student. 57, 56, 37. I'm going to add in a few of these. 35, 34, 34, 33. Probably don't have to go any further than 32, 32. 55, 54, 53, 52, 51, 50. And so the innermost two, the 50 and 51st, happen to both be the same thing. So vertically, need to meet with a y coordinate of 34. So putting this result and the previous one together, we want to meet at either, what were they? 45 or 46. And there we go. Alright. That's all we needed. And we've got our justification. We basically said part B generalizes, and then we just had to find the middle of those two lists. So that actually wasn't that bad. I was expecting C to be much worse. I was having trouble with the lists, as you saw. I just decided to count my way down rather than try and come up with some formulas. But you could probably speed it up with some formulation or something like that. But there we go. So that wraps up the 2012 Galois paper. Question 4 is a little longer than I might have thought, but decent question. I kind of like that it's the middle two numbers and that the middle two positions, and that we were able to prove that. All right, so if you're looking for more Galois, up next will be the 2013. If you would like to, feel free to join me for that.